Yes, yes, please go ahead. Yeah.
Yeah. So basically, the vinyl ester benzoquinone reactions are like vinyl derivatives are used. So that's why statement one and two are agreeable and are correct. Next, statement third is impurities present in the monomer can also act as reaction inhibitors. This is a subjective statement because impurities present in the monomer can also act as reaction inhibitors. Yes, they can act as reaction inhibitor or they cannot act as reaction inhibitor. It depends on the species of the impurity which is present inside the monomer. So that's why uh, it will be better since statement 3 is subjective and subjective to the nature of the impurity. With certainty, we can say that reaction statement 1 and statement 2 are correct. That's why statement 1 is correct and statement 2 is correct. Statement 3 is based on subjective reasoning. So we need to know the nature of the impurity. Only then we can tell if the reaction inhibitor is reaction is inhibited or not. So, in the next question, again, we have a statement-based problem. In order to carry out the spectroscopic analysis of chain polymer, if the polymer contains strong IR absorbers, then NIR, that is near infrared, will be better alternative than IR spectroscopy to obtain the linear response of the spectrum. So when the polymer contains strong IR absorbers, when does this happen is when you have an IR absorbing group or if the polymer chains are long enough that they create a very big bulk which contains strong ion absorbers. In that case, near infrared spectroscopy is much better because it is able to probe into the bulk of the polymer chains, and with that, it will be a better alternative to the infrared spectroscopy to obtain the linear response spectrum of a polymer. Because the since the polymer is present in a very high bulk, the infrared rays might get absorbed, but the near infrared rays might get scattered, and from there you can see the transmittance and reflectance for the IR spectroscopy, which is a better alternative to the IR spectroscopy. So that's why this statement is true. Third one, the next question is, solvents are the liquid substance that do not dissolve the given component of solution during precipitation of the polymer. So this is you can see that this statement is blatantly false because solvents are basically used in polymerization so that they are able to dissolve the precipitation of the polymer because the viscosity of the polymer itself is very difficult to handle. And the main purpose of adding solvents to the polymerization reactions is the viscosity is lower and the mixture of the polymer which is polymerizing can be easily operated upon because the operational problems which are caused because of the high viscosity are very dangerous because of the high viscosity what happens is that temperature regulation also becomes very difficult, so that's why we require the polymer to flow easily, and that's why solvents are liquid substances which are required to dissolve the given component during the precipitation of any polymer. So that's why this statement is false. In case of high viscosity polymers, the size exclusion chromatography cannot be used due to the clogging of reactor by the viscous polymeric fluids. So in this case, you can see that it is saying that in case of high viscosity polymers, size exclusion chromatography cannot be used. This is not true because size exclusion chromatography is the principle of size exclusion chromatography itself is based on the fact that uh, it is able to differentiate the polymers based on the chain length. So what the size exclusion chromatographic column does is it distributes the polymer in various zones. The first zone which comes out is the polymer chains with the highest molecular weight. After that comes the subsequently lower ones. And at the end of the entire polymer, when it passes through the reactor of the size exclusion chromatography, is the smallest polymer chains. Why does that happen is the size exclusion chromatography reactor has porous beads inside it. So these porous beads are called gels. These gels, or you can call it gel permeation chromatography also, that is the other name of size exclusion chromatography. What happens in these gels is since they are porous, they have very small pores. So the long chain polymers, they are not able to enter these small pores and they pass through the entire bed without any uh, passing through the pores. So they come out first. So whenever you are seeing the spectrum for a size exclusion chromatography, the first field which comes is for the highest molecular weight polymers. So the high molecular weight polymers comes out first, and then as the polymer chain reduces, these small polymer chains starts going inside the porous porous beads. So once they enter the porous beads, what happens is the solvent is flowing over it, they enter the porous beads and they come out on the other side. So this process takes a lot of time. Because of this, the residence time of the small polymeric chains is very high. And because of this, they come at the end of uh, the spectrum. They come at the end of the spectrum. Beginning of the spectrum is high molecular weight, end of the spectrum is low molecular weight. And this is the exact reason why viscous polymeric fluids are tested with the size exclusion chromatography. So the answer for this question is uh, false, because size exclusion chromatography is exclusively used for high viscosity polymers. So this statement is false. Next is, at very high concentrations of initiators, the order of rate of radical polymerization reaction RP, dependency on initiator concentration 1, can be found to be less than half. The reason can be attributed to which reason? So the first one, we have been given here three reasons: resonance stabilization, impurities present in the monomer, and cage factor. Now, you might be seeing here there is something called a cage factor. Cage factor, first I will tell you what are the cage factors. Uh, Cage factor happens when the radicals are formed from decomposition of an initiator. So when there is an initiator and it starts decomposing, it forms like it it forms the radicals itself. And these radical uh, initiator molecules are surrounded by cage consisting of solvent or monomer. So what happens is the moment this initiator is decomposing to form the radical, monomer molecules are surrounding it. So the moment the monomer molecules are surrounding it, the initiator, which has been decomposed to give a radical, will quickly attach to the monomer. So that's why at that point, the very high concentration of initiators, the order of rate of radical polymerization reaction dependency will increase on the initiator concentration. So that was the cage effect, where radicals formed from decomposition of an initiator molecule are surrounded by cage consisting solvent or monomer monomer molecules. And within these cages, recombination of radicals can take place, deactivating the reaction. So what happens in these cages is that either it can start the reaction, or there is a high possibility that recombination of radicals can take place, which will deactivate the reaction. In that case, it will slow down the reaction. And that is why you have a second portion of the sentence which is saying can be found to be less than half. So the dependency on initiator concentration can be found to be less than half. So that's why uh, pH factor is a very important property for the order of the radical polymerization reaction. So KH factor is the correct answer. And for some additional info, KH factor can be quantified as something called KH efficiency, which gives you the ratio of rate constant for the KH combination. KH combination of these cages, which is formed by the solvent or the monomer molecules, to the sum of the rate constants for all cage processes. So cage combination, rate constant for cage combination divided by rate constant for all cage processes. So that's how you get the cage efficiency. How quickly the cage factor is working and how efficiently it is able to combine the uh, recombination of the radicals. So cage factor is the main factor for reducing or deactivating the initiator concentration. So cage factor is the answer for this question. Next one is, the selection of an initiator depends upon the operating conditions such as reaction temperature and rate of the homolytic cleavage. So this is a pretty straightforward question, and yes, the dependence of initiator is on the operating conditions such as temperature and the rate of the homolytic cleavage. So how fast the homolytic cleavage is occurring, that takes the prominence, and the reaction temperatures also uh, play a major role in selection of the initiator species. That's why this statement is true. Most of the questions in today's class are more or less based on theory. So it is uh, mostly about the reaction mechanics, how the reaction are proceeding. So if you read about the polymerization processes, you will be able to answer most of these questions. I think the lectures for this week have not yet been released, or they have still to be released. So that's why you will be having some doubts regarding these questions. Sir, I think you wanted to say something.
Nothing. Yeah, please go ahead. Yeah, I have gone through it. No issues. Yeah.
Yeah. Okay. Yeah, that's all there is to it. So in today's class, we saw that basically it was more about the reaction mechanics and the bond associations, and it was basically related to the radical polymerization reactions and how Kh factor and what are the different mechanisms involved during each step of the initiation, propagation, and termination of a radical polymerization reaction. So from next class onwards, maybe there will be more things about the solvent, maybe solution polymerization or the ionic polymerization reaction. So these questions are mostly based on the details of the process itself. So if you go through the process details, you'll be able to answer these questions much more effectively.
Yeah, got it. Actually, this is like a general information is only understanding. Only thing, just I
Yeah.
want to clarify this thermally initiated must having a bond energy of 100 to 170.
Hmm.
That is with respect to like different types of bonds is there. Like we are talking only about covalent bonds here, right?
Covalent bonds. Yes, specifically covalent bonds.
Okay, okay,
Hmm.
okay. Fine, fine, fine. Then
Hmm.
this is a reasonable number, like one
Yeah.
100 to 70. Yeah.
Yes. Yes. Uh, okay, sir. So if you don't have any doubts, we can end this
Yeah,
class.
fine. Yeah, fine. Thank
Yes,
you.
sir.
Because actually there was one parallel session for this also going on.
Okay. Okay.
So I was going through this session, then immediately I thought I will shift to that other one. All right.
Yeah. Yeah. It's
Thank you.
fine. Yeah.
Thank you. Thank you. Thank you. Bye.
Yes. Okay. Partha, if you have any questions, maybe.
Actually, I was only listening to
Hmm.
these all the questions like you are explaining, na? But
Yeah.
I could not able to too much into the discussion part or anything like I was getting all the questions. Actually, I'm in the middle of the audit is going on in my office, BIS
Oh.
office. Actually, BIS audit is going on. So I
Okay.
could
Okay.
not even wanted to. I don't want to miss the class. That's why I was attending, but could not.
Oh. Okay. 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 Okay.
Yeah.
It's fine. It's
So
okay.
I
It's
was I
okay.
was reading the question and I was checking the answers like you are explaining and I was listening in between and also concentrating on my work also.
No, no, it's okay. It's okay. No problem. No problem. If so, you're still in office right now.
Yeah, I am still in office and I don't know how much time it will continue.
Oh,
The
or
BIS
yeah,
actually audit is going on in our laboratory.
yeah. Definitely, audit takes a lot of time. I know that.
Yeah, we are having actually NABL approved laboratory. We are having NABL approved laboratory of all plastics polymer related testings.
Okay. Okay.
And now we are going to be after this audit, we will be BIS approved. Now we will be
BIS approved
certification body for the plastic BIS approved certification body for the plastic uh, uh, products like
products.
pipes or any kind of products.
Mm-hmm. Okay, that's very nice. That's very nice.
Yes, yes.
So that is good. So like this separate, which where is this separate? It's in Roorkee,
Actually, we have total more than 40 centers all over India. So
India. Okay,
I'm in Dehradun. I'm in
Dehradun.
Sipet Dehradun. Center situated in Dehradun.
Separate Dehradun. Okay, that's good. Like, if you don't mind me asking, like, what is the procedure to get a job there or something like
Procedure to actually in time to time paper advertisement comes,
that?
and
Yes.
all the selection procedure and everything is conducted by Sipet only.
Hmm. Okay.
There will be based on the advertisement, there will be a particular day for the written test, and eventually there will be next for call for interview.
Yes, yes, yes. Okay.
And it is not location specific. They may select for a particular. They may post in any of the places. Like
Mm-hmm.
wherever shippers are there, they will
Place you there.
they may yeah, they do the posting.
Okay. So, like, CPET is mainly focused on polymers or composites or anything?
Yeah, mainly petrochemicals. We are earlier
Petrochemicals.
the CPET was Central Institute of Plastics Engineering and Technology.
Hmm.
Now it has become broadened. Like
Broadened.
the name has changed to Central Institute of Petrochemicals Engineering and Technology.
Okay, okay.
So in
Okay.
petrochemicals, so many things as is covering. It is not only plastic polymer. It is covering so many things.
Okay, okay.
So it has broadened the thing. But earlier it was like it was plastics only. So
Hmm.
that plastic thing is we are more dominated or plastics.
Hmm. Hmm. Yes, yes. Okay, okay. Okay, that's nice. That's nice.
Yeah.
So, like, uh, yeah, that's good. So, you
So
want me to?
maybe next week classes I will be more like will be concentrating on the classes that will be like explaining. Today
Okay,
I
okay.
have
No, no, no
screenshotted all
problem.
the questions.
Yeah, yeah, no problem. No problem. It's fine. It's fine. So, like, if you have any doubts, you can like write to me, or like you can put it in the NPTEL forum itself. There it will be answered.
Yes, 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 yes. Or
Mm-hmm.
maybe next class or anywhere will
Hmm.
be like I'll definitely.
Definitely, definitely. In the next class itself. Okay.
Okay, okay, okay.
Okay. Thank you. Thank you.
Okay, okay. Thank you, thank you. Bye.
Yeah. Bye. Till nucleation of homogeneous and heterogeneous mechanism. Hello.
Just a second, just a second.
Yeah,
Actually,
yeah, yeah. It's fine.
yeah. Yes, yes, yes. So sorry, actually, I am still in office, no. So
Oh, okay, okay.
in between, one person has come to ask something. Yeah, yeah,
No, no, no. It's okay. It's okay. Like, if you are like just finish that work, then we can see this.
yeah. He has gone actually. Already finished.
Oh, okay, okay. Yeah. So you have gone through the lecture, right? This
Yeah.
exam. Uh, so you should be able to answer the first question, I guess.
Homogeneous and heterogeneous. It is the case when homogeneous is when the monomers are completely soluble,
Hmm. Yes.
and during heterogeneous when there is not so much of uh, solution has been taken place.
Yeah, yeah.
For both the cases, like you have mentioned, the monomer are water soluble.
Yes, yes, yes. So it will be like that only.
Uh, Related to heterogeneous,
So the so how will that be? What is the criteria for homogeneous and heterogeneous structure?
uh, I think the homogeneous is a situation when there is a complete uh, solution of the particle
Hmm.
monomer,
No, in
and
both cases, that is true what you said, that monomers are water soluble. So at that time only it will dissolve. Like it will, nucleation will occur in that case. So the first
yeah,
option that the monomers
yeah.
are water soluble is correct. Then if you explore the other options also, then you have to find out what is the CMC and how the micelle formation is going to affect.
Mycelia is when it formed when there is a surfactant.
Hmm. Correct,
Uh,
correct.
the surfactant in the surfactant monomer gets in the
Hmm.
micelles, this monomer get trapped inside, and
Yes.
we add surfactant to uh, untrap the monomers from the micelles.
Yes, correct, correct. So the concentration of surfactant is very high, so that the micelle formation can occur easily is also the other reason why it will occur. Okay. So the first option and the fourth option is the correct answer for this question. Okay. We'll move on to the next question. Which factors affect the molecular weight distribution in emulsion polymerization? So now we have the molecular weight distribution. So what will affect the molecular weight distribution?
Molecular weight distribution would be depend on the initiator and the concentration.
Yes. Can you explain like in what manner?
The molecular weight distribution taken it would be dependent on how much we are initiating the polymerization. Like it all
Hmm.
keep on getting chained. like in a linear form, it is getting added.
Yes,
Polymerization is
yes.
taking place, and
Hmm.
there is a oligomer or free radical gets polymerized with one another,
Yes,
and it is keep on going. So in that case, the molecular weights distribution would increase.
yes, you're right. So that is the one of the main reasons why molecular weight distribution is affected in emulsion polymerization process. Okay. So
Okay.
next one, yeah, next one is the advantages of operating emulsion polymerization under limited monomer supply maximizes the production rate. And so this is a pretty straightforward question, and you can tell that this statement is false because if you have a limited monomer supply, it is not like it won't be able to maximize the production rate. The yield won't be maximized.
Exactly.
Yeah,
Exactly.
definitely. Hmm, exactly. So we will just go to the next question. This is also a formula-based question only that the
Uh,
amount of surfactant. Yes.
in this case, actually, I found there are so many direct formula
Hmm.
uh, during the lecture I come across.
Yes, yes.
So it is just like we have to learn directly.
Exactly, exactly.
Just
It's a direct formula.
memorize the formula. That's it.
Yeah, because there it's like a direct relationship between for the heterogeneous nucleation, how it is occurring, and this is the first one. The first option is the correct formula. That is SW is equal to ST minus AP star by AS, where NM, sorry, SW is the amount of surfactant that is dissolved in aqueous phase, which will form the micelle. SW can be calculated by means of overall material balance. That is the and ST is the total amount of emulsifier inside the reactor. So ST is what is present inside the reactor. AP star is the total surface area of polymer particles. How much it's available, that is the okay. So with respect to that, we are calculating it. So you'll have to just know the first formula itself. The definition of the individual parameters is given right here. APAS, you can see that. Okay. So the first one is the correct answer for this question. Next question is
Okay.
the rate formation of particles by homogeneous nucleation is the rate at which the radicals growing in the aqueous phase exceed the maximum soluble length. So you can see that the rate formation of particles by homogeneous nucleation, it is asking us the rate expression or the rate formation where you can see homogeneous nucleation is occurring. So the oligoradicals, which are uh, oligoradicals growing rate in aqueous phase, which when exceeds the maximum soluble length, it will give you the rate of formation of particles. So this is
After
true.
that, it will become heterogeneous.
Yes, exactly correct. After one point, it will become
When the
heterogeneous.
oligo radical gets
Hmm.
exceed the maximum soluble length,
Yeah, exactly. So that is the critical length. The critical length depends upon the composition of the oligoradical. So based on that, the differentiation between the radicals value from initiator and the other radicals help to define the composition. So the critical length is very much dependent, which will decide your homogeneous or heterogeneous part. So this statement is true.
okay.
Okay.
Sarvan
So
sir, we have been waiting for you.
yes, sir.
Hello, good evening.
Yeah, good evening, sir. We have been waiting for you actually.
Sorry, I was a bit late. Last week I could not join. I was in a tour. Sorry for that.
Oh no, it's fine. It's fine. We are actually just going through the questions from last week
Yeah, yeah,
only
please. Yeah.
because apparently this week's lecture has come late, so that's why we are just going through questions of this time. So So yeah, so again, now it is like we have a question that what are the ways to remove residual monomer which is formed? So what can be done to remove the residual monomer? If we have gone through the nodes, you can answer this one.
Devolatilization is there.
Yes, devolatilization is there. Correct. That is one important process.
And post polymerization process.
Correct. Post-polymerization process consists of inverting fresh radical generating system to polymerize the remaining monomer at the completion of main polymerization process. So what we are doing is when the polymerization is over, if any leftover polymer chains are there, we'll introduce some fresh radicals and polymerize them also. Okay. So the answer for this question is 1 and 2. Points 1 and 2. Okay. So
Uh, like fourth point. Suppose we
yes.
add fresh radicals.
Hmm.
So in that case also that residual monomer get polymerized
No, no.
can be done.
Uh, Actually, we are adding this in the intermediate stage. So at intermediate stage, you cannot tell how much residual monomer will
Yes,
remain.
yes, 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 yes,
Yeah.
yes.
So that's why you have to like wait till the polymerization is over, and after that you then release it. Okay.
Okay.
Yeah. Moving on to the next question. Linear emulsion polymer can uh, only be formed if the average number of radicals per particle is greater than zero point 0.5. So this is like a
It's kind of direct question
direct question. Yes, it's a direct question.
from the equation.
Hmm, exactly. It's a direct question, and you will have to remember that it's it's not greater than zero point 0.5. It will be less than zero point 0.5 like that. We'll have to remember this part. Okay.
Yes.
Yeah. How are linear polymers formed in absence of chain transfer mechanism? So we saw the like we know the how it happens is that since chain transfer mechanism is not there, chain transfer means transferring the activity of one chain to the other. So if activity is not being transferred, it won't group. So basically, linear polymer formation, how we can how it is formed is using the monofunctional monomer unit. So if monofunctional monomer unit is there, only single functional group is attached with the participating molecule. So that's how it's going to increase in length.
The presence of monofunctional monomer unit will lead to the linear polymer formed.
Yes, increase in the length of the linear polymer. So that will be helpful in increasing the length of the linear polymer.
Lengthwise it will get polymerized.
Yes, yes, exactly. Moving on to the next question. Which two forces control interfacial polymer migration? So now it is asking us how the interfacial migration is being controlled. So here we have first van der Waals force, then viscous drag, then we have cluster formation, radical attachment on the outer layer or the outer layer of the new polymer. So you can,
In this, like I wanted to ask,
yeah,
here the polymer migration indicating what? The polymer migrating from which part to which part? That one actually I was like wanted to know
yes, yes,
actually. Know actually.
yeah. So what happens is that in polymer in polymer migration, right? First of all, we need to understand how it is happening. Basically, the polymer reaction can be found to occur at both regions. It is happening in the cluster as well as inside the polymer matrix in the interface region when it is being formed. Uh, Polymer matrix in the sense like when you have the emulsion form. In emulsion, you have the dispersion phase and the dispersion medium. So if radicals attach on the outer layer of polymer particles, new polymer will form on the periphery itself. If you have a polymer molecule like a circle or a bead, sphere bead, the radicals which will attach on the outer layer will start growing the polymer there. And if the polymer starts growing on that polymer itself, it will form a cluster plate. Okay. So it will result in some sort of cluster. So what happens is increasing the concentration of newly developed polymer chains, phase separation will occur, which leads to cluster formation. Definitely, if the amount of polymer which is growing on the side of that already existing polymer will make a huge mass and it will separate out. It will become like a single entity and it will separate out. Okay. So
It will
how
get
will,
precipitated.
yeah, kind of. So what happens in this is that polymer migration results to increase the size of cluster due to polymerization in the cluster itself. When the cluster is formed, it will continue polymerizing there and diffusion of the polymer into the cluster. It will keep diffusing different polymers inside the cluster and it will coagulate. It will just form a clump with other clusters. So it will just become like, it will be localized. It won't be spread everywhere. It will just form the cluster in one corner and it will increase a lot. So this migration is governed by basically two forces. First is van der Waals force of attraction and repulsion, and the second one is viscous drag. So that is the answer for these. How that affects is van der Waals force between cluster and aqueous phase can be attractive. So if these two forces are attractive, it will shift the cluster towards the surface of the particle. Okay, it will just bring it to the surface of the particle. And if it's repulsive, it will move the cluster to the center of the polymer particle. It's like that. If it is surrounded on all sides, then it will shift how it is going to attach onto the polymer. When and also the van der Waals forces are proportional to the interfacial surface tension, which is formed in the emulsion polymerization. Since we have the dispersed phase and dispersion medium, there is an interface force between these two. So your van der Waals force is kind of balancing the interfacial surface tension. So in that case, it swings between attraction and repulsion. And apart from this, when we come to viscous drag, the resistance to flow is arising from viscous drag. If the particle is very high, like very large, or the polymer cluster is big, then it will have a lot of viscous drag, and because of this, interfacial migration will be hindered because it will be experiencing more drag, so the velocity at which it will migrate will be low. Okay, so what happens is that if the internal viscosity of particles are high, then like a semi-stable morphology will be. Uh, Low interfacial surface tension will promote the grafting reaction. Grafting reaction means what? It will graft, like it will form a layering that is called grafting. It will attach onto it and form a graft. So that's like a grafting polymerization process. On the other hand, if there is low internal viscosity, and that time equilibrium morphology can be achieved. In this case, the interfacial tension will be very high, and because of this, instability can be occurring inside the solution itself. Since the
Uh,
interfacial, yes.
just one thing. Sorry to interrupt. Here, this migration indicating whether it's a after the polymer get reached to a critical length, so
Hmm.
it get come out or get segregated from that particular point, and
Yes,
it reached
exactly.
to that point where we call it sedimentation or precipitation.
Uh, you can call it phase separation. It will just separate
Phase
out.
separation. Yes, yes,
Yeah,
yes, yes, phase
yes,
separation.
sir.
So that phase separation part is called as a migration, or is it something else?
Yeah, it is exactly that. That's how it is going to migrate. Because as the polymer forms, it has to spread inside the entire dispersion medium, right? So dispersion phase is there. And then once the polymerization starts, it has to migrate everywhere. So that's how the polymer migration process takes place. So what is stopping this migration, or what are the factors which affect this migration, is what it is. So
That one is like viscous drag and van der Waals forces, like you
yes,
mentioned.
exactly,
And one more
exactly.
thing that I've noticed in this question, like
Yeah.
what I was thinking, here it is told two forces. Which are two forces? Like forces
Mhm.
they've already mentioned, and in the
Mhm.
option we can see this cluster formation is not a force, or radical attachment on the outer layer of a new polymer is again not a force. So it
Yes, yes,
becomes pretty obvious that
yes,
van der Waals force and drag, viscous drag is kind of force only. It's a
yes,
surface force. So
exactly, exactly.
from that point of view, I think uh, I
It will
don't
be
know whether
easier.
it
Yes,
is
yes.
relevant.
Yeah, but it depends. Like if the wording is changed, then you will be confused, right?
Yes, yes, yes. In
It's
that
just
case, I'll
about
be
the.
confused. Yes.
Yeah. And I think it is supposed to be a direct question because in the notes also you can see that it is directly given that it is governed by two interfacial forces. So you can directly see it. Okay, so moving on to the next question. Which reactors can model the Cout-Taylor flow reactor? So we have the Cout-Taylor flow reactor shown, Cout flow scheme shown here. What happens in Cout flow is that in Cout flow, either the outer cylinder is stationary or the inner cylinder is stationary, and one of them is rotating. So what happens in this? You're going to put your polymerization mixture inside the annular space. So in the annular space, when the inner cylinder starts rotating, there is a gradient formed between the wall and the center. So you can see right here that near the wall, and near the center. So the velocity of the fluid layer, which is very close to the centermost point, it will have the maximum velocity, and the one which is at the stationary wall, it will have the lowest velocity. Okay, so because of this, what will happen is that the Taylor number, there is a factor related to this called Taylor number, where initial inertial forces due to rotation divided by the viscous forces are involved. So when your polymerization is rising, definitely viscosity change is there and inertial forces due to rotation. So to allow mixing, what happens is the inner cylinder will rotate faster and it will be responsible for your mixing divided by the viscous forces. So that defines your Taylor number. So what happens is as the viscosity change follows a particular trend, Taylor number will be modified by the cylindrical by modifying the cylindrical outer cylinder with a conical one. You can change the Taylor number inside. And since we are talking about mixing, the mechanism of Cout-Taylor flow is similar to that of mixed flow reactor. Since mixing is taking place, right, and it's continuous mixing on the edges, and because of the gradient which is forming, since the viscosity gradient is forming because of the fast mixing and polymerization occurring at simultaneously at the same time. This flow is similar to that of a continuous stirred tank reactor in series. So the answer for this question is continuous stirred tank reactor. What happens is that when the inner cylinder is rotating, the liquid or the polymerization mixture which is present in the middle will counteract that force. Definitely, it will show some resistance to flow, that is viscosity. So that resistance to flow will create counter-rotating toroidal vortices. Counter-rotating toroidal vortices means Because of the resistance to flow, as the inner cylinder is rotating, the liquid will try to resist it in the counter direction, and because of that, small vortices are formed. These small vortices signify a single stirred tank reactor. So you can imagine that as multiple stirred tank reactors in series. So the analogy is something like that. So if you are able to like catch that analogy, then you will understand that continuous stirred tank reactor is what it is being talked about here. So Gaut-Taylor flow reactors show behavior of continuous stirred tank reactor. Okay. If you have seen the diagram and the explanation for it in the course notes, then you will be able to understand it much better, I would say. Here, what I have shown is just a small representation.
It will work as a continuous.
Yes, it will work as a continuation because the inner cylinder is rotating continuously at a particular velocity, and small toroids are forming in series on the outer cylinder itself because of the velocity. These toroids are forming. Why? Because there is a mismatch between the inertial force due to rotation and the increase in viscosity. Because of the increase in viscosity, there is a resistance, and the inertial force of rotation is going to push it this side, and viscous force will push it on this side. So there is a formation of a vortex. So small vortexes are being formed. Because of that, it is giving it a continuous stirred time behavior. So that is being described. Okay, it might take some time to understand that, but that's how it is.
Uh, just one question.
Yeah.
Uh, Suppose continuous stirred tank reactor indicating we are continuously feeding monomers and other radicals and all these things continuously inside the tank, and
No, no.
and in the tank it is getting reacted, and the polymerization, the output we are getting the polymerized product.
Polymer. Yes.
Okay,
Mm.
so here like the desired molecular weight product or desired product which we wanted,
Hmm.
whether is it possible in this
Setup.
coated Taylor coat Taylor flow reactor?
It is possible. Actually, for emulsion polymerization, this will be very much important. Why? Because since we know that there is dispersed phase and dispersion media, it is important to facilitate the reaction with some rotation, definitely. And when you create such an annular space, the annular space which is created here,
Here
that
in
is,
place of stir, we are using inner cylinder.
yeah, exactly. So what it does is that it is creating a lot of what should I say, gradient forces in the middle of these two layers, the inner cylinder and the outer cylinder. So in that case, the reaction will be quite fast, and we will be able to achieve our desired yield also.
Okay.
Hmm. So if the what happens is that, but the main problem because of this is that uh, coagulation can occur. Why? Because since the annular space is there, so if the polymerization mixture increases a lot, your viscous forces will overpower the rotational forces, and sometimes because of that, the polymer might settle down. So that is one of the problems which can be faced in this case. Okay, so remember these things because these are the small things which can be asked for as questions in the exam. Okay.
Okay.
Yeah. Okay, then that's all it was. That just this was like more like a revision class because we haven't gone through the this week's new lectures, so that's why.
There is one question.
Yeah,
uh, which was came across. So just
yeah,
share
yeah,
that question?
yeah, yeah, yeah.
Just a second, just a second. Let me just see the question, what exactly it is saying.
Is it related to emulsion polymerization?
Yes, yes.
Okay.
This week, related to this week.
Yes, yes.
Just can we scan through the initial questions if you don't mind?
Yeah, yeah, yeah. Sure. Before you came, only the first question with like one, two. Yeah, only the first three questions we discussed around. So the first one was that particle nucleation will occur due to both the homogeneous and heterogeneous nucleation mechanisms if choose the correct answer. So what happens in homogeneous and heterogeneous nucleation processes is that it the homogeneous and heterogeneous during homogeneous and heterogeneous nucleation, monomers should be water soluble. Only then the nucleation process can proceed. So in the four options, we can see that the first one is the correct answer, but we have to see the other options also. In heterogeneous and homogeneous nucleation process, the
Just a
formation.
small request. Can we, sorry to interrupt, can you make it in slideshow mode so that the points are
Oh,
very. Yeah,
okay.
yeah,
Now is it visible?
yeah, fine, fine. It is clear.
Yeah. So in heterogeneous or homogeneous mode of nucleation, the there are different factors which are responsible for the nucleation mechanism. First is that the first condition which should be applicable for the homogeneous and heterogeneous to occur is the monomer should be water soluble, and on top of that, the micelle formation because of the surfactant which has been added should be high enough so that micelle formation can occur easily. And since if micelles are not present, the emulsifier will form through the existing polymer particles. So that's why the concentration of surfactant should be high enough that micelle formation can easily occur. And emulsifiers are generally used for stabilizing the particles formed through homogeneous separation. So that's why the fourth option, the concentration of surfactant is very high that the micelle formation can occur.